Hi everyone, this is Mengxi, and today I will be talking about learning user preferences for assistive robot teleoperation to enable intuitive robot control. In our everyday life, we see a lot of cool applications of robot teleoperation. For example, many of us have used a joystick controller to play games. But teleoperation shows up in other applications too, like robotic surgery or teleoperating a robot to explore the deep sea. More recently, we have seen teleoperation used in domestic domains as well, such as assisted feeding for patients with disabilities. For some robotic systems, controlling them is really simple. For example, for this toy car lifter, it can only go up or down. With only 1 degree of freedom, it's clear and also easy to control by just pushing and pulling. However, for some other more complex systems, controlling them might be more challenging. On the right, when the user is trying to manipulate the flexible robot arm, which is a joystick in the hand, they might have a hard time understanding how this complex control system works. Well, while this sounds challenging, it's not impossible. There already exists a bunch of works looking into different ways to achieve this. To make up for the limitations of the low-dimensional controller, some propose that the controller should change modes between different degrees of freedom using the translation mode, rotation mode, and finger mode, which is controlling the gripper. And then the user would need to switch between different modes to achieve their desired robot movement. There are also other works that try to get rid of this discontinuous mode switching by learning a continuous mapping from a low-dimensional latent action space to the high-dimensional robot action space using autoencoders. However, in all of these works, an underlying assumption is that the mapping between the user input to the robot actions is one size fits all. Let me explain what I mean by that. Imagine a setting where the user is using one of the strategies to control the 7 degrees of freedom fetch robot with the 2D joystick. And then they're trying to put the apple to the trash bin. Here, when the user presses down, the robot arm moves back. However, what this user thought is that pressing down would cause the robot arm to move down as well. So here, what other people thought is intuitive might not be as intuitive for this specific user. Or in other words, different users might just have different expectations of how we should control the robots. And thus, this one-size-fits-all control strategy does not work well for all users. So in this project, our goal is to learn personalized control strategies for assistive teleoperation from humans in a data-efficient way. Now, let's formulate this problem. Let's say we have a human interacting with the low-dimensional joystick and a high degrees of freedom robot, and we have a controller to connect them. When the robot is at state S, the human gives an input H by pushing the joystick to the right. Then the controller would map that to the robot action A, and then the robot arm rotates down. However, let's assume there's a coffee mug on the right and the human wants to get that. So the user thinks that he should press right because intuitively he thinks pressing right will cause the robot arm end effector to go to the coffee mug. Well, if we don't do anything, the naive control is to plug in the human input H, go through the predefined controller mapping fee, and we get an action. This might not be what the human actually intended. Instead, we could also try to be more intelligent. When the user is pushing to the right, the robot will reason about this and think, what's the actual corresponding control signal that will map to the user intended robot action? So in this case, even if the user is physically pushing to the right, the control signal is not exactly going to the right. And it can be moving to the upper right so that the robot arm end effector is in fact moving to the coffee mug. Our goal here is to learn an alignment module that discovers the mapping between the human input and the control signal. Here, we use a general feed-forward neural network to model this mapping. And we query the users to collect data for the training. First, the arm is moving to initial state S1. And then we randomly sample a next state S2. We ask the users to give their preferred input if they want to control the robot arm moving from S1 to S2. In general, training the neural network requires a lot of data, and this can be expensive or sometimes even infeasible when training with real humans. So our key insight is to learn personalized control strategies in a data-efficient way by enforcing a set of desirable and intuitive priors. We propose some intuitive priors that can facilitate the training. These priors are some properties that we expect an intuitive system to have, and we incorporate them in our training for semi-supervised learning. The first thing I will be talking about is proportionality. What proportionality says is that the amount of change in the 3D pose of robot's end effector should be proportional to the scale of human input. If the human pushes to right with offset h, the robot arm would move delta x. Then, if the human input is alpha h, the corresponding movement should be alpha delta x. Formally, here, psi is the mapping from robot state to the end effector pose. If delta x is the end effector pose change with human input h, then when the human input is scaled by a factor alpha, the pose change will be scaled by alpha as well. And we penalize the deviation to alpha delta x with a quadratic loss term. Then let's define reversibility. If there exists an action h that makes the robot transit from S1 to S2, then as S2, the opposite action negative h would make the robot transit from S2 to S1. Formally, it means that an input h and negative h will make the robot transits between S1 and S2. So if we start from state S, give a human input h, and then followed by a negative h, the state should go back to original S. We also construct the corresponding semi-supervised loss term for reversibility by adding a quadratic cost. We also have a third property named consistency. Let's define consistency. The same action taken on similar states should lead to a similar amount of change in the 3D pose of robot's end effector. For example, in state S1, human input h would make the robot arm move delta x. Then, in a similar state S1 prime, the human input h would also cause similar change delta x prime. Formally, we look at the end effector pose change delta x1 and delta x2 for state S1 and S2 respectively. If S1 and S2 are close, then the delta x1 and delta x2 should be close as well. Correspondingly, we define the consistency loss to be this. We compute a similarity score between pairs of states and use it as a weight for the square difference penalty, so that the end effector pose difference for similar states would lead to higher cost. Now we have all the priors, let's put things together. This is our pipeline. Compared to naive control, we add a learned alignment module to interpret the human's physical input to the corresponding intended control signal. To efficiently learn this alignment module, we leverage semi-supervised learning. Here, the total loss would be the supervised loss with labeled data plus a weighted sum of the loss with our 3 intuitive priors. Here, the first term is a supervised loss, and the 3 are our semi-supervised loss. We conduct a variety of experiments using a manipulator. Let's first look at the playing task. In this task, the user will control the robot arm to move in a 2D horizontal plane. There are some obstacles here, and they try to circle this in a clockwise and counterclockwise direction to avoid the obstacles in the middle. We first conduct experiments in simulation with simulated humans that have different levels of noise and compute the relative error for the end effector position. Across all of the noise levels, the no alignment and manual alignment have large errors. The ideal alignment is the fully supervised model trained with sufficient label data and basically the best we can do. If we add the learned alignment model, but only have supervised loss and no priors at all, it can do better, but still the error is not very low. And then we experiment with each prior separately. We can see they effectively drive the error down with a margin. And finally, if we combine all the priors, our model can efficiently learn the mapping with a few curves needed. We then also conduct a user study with a 7 degrees of freedom Frank-Capella arm. For the playing task, we can see our method shows lower task completion time and shorter trajectory lengths. The input change term captures how much counteractive inputs the human is giving. Lower values demonstrate that our model is easier to understand so that the users save some efforts. We also conduct our experiments in more challenging tasks. For example, in this rich and poor task, the user would be asked to teleoperate the robot arm to achieve the yellow cup, and then pour into the orange bowl. We get similar results here. Our method works consistently better in both simulation and the user study. Let's look at an example. For no alignment, the user struggles to do the task. With no priors, the behavior is slightly better. And with our model with intuitive priors, the user completes the task much more smoothly. Here are the visualized trajectories. It's also clear here, our method results in smooth trajectories and saves a lot of user efforts. Finally, we collected some subjective feedback from users as well. Users thought that our learned model with intuitive priors aligned with their preferences, was easy to control, and improved efficiency. Plus, they would choose to use it again. In summary, our goal in this project is to make teleoperation understandable and personalized. We achieve this by proposing to learn an alignment model. To do this in a data-efficient way, we formalize 3 intuitive priors and develop corresponding semi-supervised losses respectively. Our results in simulation and user study both demonstrate that our methods can efficiently learn the alignment and help with the task completion, and users prefer them. Thanks for listening.